Hey there. We use the word work all the time, right? A hard day at work, working out, the work it takes to study. But what if I told you that in physics, work has a super specific and honestly a really beautiful meaning? Today we're going to dig into what that is, and you'll see how it connects everything from pushing a simple box to the very nature of energy itself. So let's forget the everyday definition for a minute and find the one simple rule that explains how things get moving in our universe.
So here's the game plan. First, we'll nail down what work actually is in physics. Then we'll throw some weird paradoxes at that rule to see how it holds up. After that, we'll uncover the huge connection between work and energy, figure out where power fits into all this, and then, finally, see why this whole concept is like getting a new pair of glasses to see the world.
All right, first things first, what is work? Let's lay down the fundamental rule of the game. Okay, think about this for a second. You've been studying for hours. Your brain is fried, you feel totally wiped out. Biologically, you burned a ton of energy. But, according to a physicist, did you do any work on that textbook just by looking at it? The answer might not be what you think.
And here's the reason why. In our day-to-day lives, work is pretty much any kind of effort. But in physics, no. Work only happens when a force you apply actually makes something move. If there's no movement, there's no work. It's this direct, unbreakable link between a force and a distance.
So this is the magic formula. Work equals force times distance. W equals Fd. But, and this is the part that changes everything, the object has to move in the same direction as the force. That one little detail is the key.
Let's make this real. Check this out. Someone is pushing a box with a force of 30 newtons, and the box slides 5 meters. You just multiply those two numbers together, 30 times 5. That's 150 joules of work. And joules, by the way, that's the unit we use for work. See? Super straightforward.
And if you're ever tackling a physics problem, using a system like the GUESS method is a fantastic way to keep your thoughts organized. But let's get back to the idea itself, because this is where it starts to get a little weird.
Okay, so we've got our rule, W equals Fd. Now let's explore what I call the zero-work paradox. These are situations where you can pour in a ton of effort and do zero work.
This is the classic example, right? You can lean against a solid brick wall with all of your strength. Your muscles are screaming, you're sweating, you feel totally exhausted. You are definitely applying a force. But in the language of physics, you've done absolutely zero work on the wall. How is that even possible?
Well, it all goes back to our formula. The wall didn't move an inch, right? Its displacement, that d in the formula, is 0. So it doesn't matter how much force you use, 1,000,000 newtons. If you multiply it by 0, the work done is always 0 joules. No distance, no work, period. And here's another mind bender. Let's say you're carrying a heavy backpack across a room. To keep it from falling, you have to apply a constant force upward, fighting gravity. But you're walking forward. Because the force is up and the distance is forward, they're at a right angle to each other. That lifting force you're applying is doing 0 work. Wild, right?
So we know work needs movement. But why? What is actually going on when work is done? Well, here's the big reveal. Work isn't just about pushing and pulling over a distance. It's about transferring energy.
This quote absolutely nails it. Think of it this way. Energy is like the money in your bank account. An object can have energy. Work is the transaction. It's the wire transfer. It's the process of moving that money from one account to another. You don't have work, you do work. And when you do, you change an object's energy.
And there's an official name for this idea, the work-energy theorem. It basically says that the amount of work you do on something is exactly equal to the change in its kinetic energy, that's its energy of motion. So if you do 100 joules of work to push a skateboard, you have given it exactly 100 joules of new kinetic energy. They are literally two sides of the same coin.
And here's the really cool proof. You don't even need complicated math. Just look at the basic units. The formula for kinetic energy uses mass, which is in kilograms, and velocity, which is meters per second squared. When you put it all together, the fundamental unit for energy is a kilogram meters squared per second squared. Just keep that weird unit in your head for a second.
Okay, now let's do the exact same thing for work. Work is force times distance, and force is just mass times acceleration. So when we break that down into its basic units, kilograms, meters, and seconds, what do we get? We get kilogram meter squared per second squared.
They are identical.
That is not a coincidence. This is the universe basically telling us that work and energy are two different ways of talking about the exact same fundamental thing. And to make life easier, we just give that thing a simple name, the joule.
So, if work is the transfer of energy, there's a really obvious next question, right? How fast is that energy being transferred? And that brings us to our final big idea, power.
Power is just how fast you get the work done. The formula is simply power equals work divided by time. A powerful car engine isn't necessarily one that can do a lot of work. I mean, given enough time, a tiny lawnmower engine could eventually move a car. A powerful engine is one that can do that work very, very quickly. It's all about joules per second.
And this table shows it perfectly. Look, Maya and Bob climb the same stairs. They have the same mass, so they do the exact same amount of work against gravity, 7,200 joules. But Maya hustles up in about 34 seconds while Bob takes a full 90 seconds. Because she did the same work in way less time, her power output, which we measure in watts, is way, way higher.
Okay, so let's tie this all together. Why should we care about separating our everyday idea of effort from the physics of work? Because when you do, you get this amazing toolkit for understanding how energy actually moves and changes the world around you.
So here it is, your new physics toolkit. Just remember, work isn't just trying hard. It's a force moving something over a distance. And the most important thing, doing work is just a fancy way of saying you're transferring energy. That's why they share the same unit, the joule. And power, measured in watts, is just telling you how fast that energy transfer is happening.
So the next time you see something move, a car, a bird, anything, try to remember what's really happening. That's not just motion. That's work being done. That's an energy transfer. Now that you have this new way of seeing things, look around. Where do you see the most powerful transfers of energy? Is it in a massive lightning strike, a rocket launching into space, or maybe it's in the quiet, incredible work a single plant does, turning sunlight into life? Where do you see the physics of work in action?